Hello ladies and gentlemen, today we are talking about section 7.1, which is applying the Pythagorean theorem. And many of you should remember the Pythagorean theorem. We've used it, or you've used it for years in middle school, possibly a little bit in Algebra 1, but for sure we'll be using it this year in geometry. Now, the Pythagorean theorem that we've all come to know and love is c squared equals a squared plus b squared. However, that's not the way that Pythagoras, who invented the theorem back in ancient Greece, would have thought of it. He thought of it literally as squares. In a right triangle, he would literally take one side and form a square, and the other two sides and form squares. And if you added the area of this square and this square, it should equal the area of this square. That's the way that Pythagoras thought of it because algebra had not been invented yet. But we know it as a squared, or c squared equals a squared plus b squared. So if we know two sides of a right triangle, we can find the other one using this Pythagorean theorem. It only works for right triangles. It only works if we know two sides and want to find the third one. Also, note that C is always your hypotenuse. It's across from your right angle. A and B are our two legs. It doesn't matter which one you call A and which one B, because when you add them together, it won't really matter. So let's do a couple of examples. Number one, find the length of the hypotenuse of the right triangle. So we'll start with our Pythagorean theorem. C squared equals a squared plus b squared. And we need to identify what C is. Is it x, is it 8, or is it 6? In this case, it's going to be x because that is what is across from our right angle. So x is our C, it's our hypotenuse. And then A and B are 6 and 8. Doesn't matter which one's A and which one's B because when we add them together, it won't matter. So our left side stays the same, and to simplify our right side, 6 squared is 36, and 8 squared is 64. When we add those together, we end up with a sum of 100. In order to simplify this, because x is not by itself yet, we haven't found the length of our hypotenuse, we need to get rid of that square. In order to get rid of a square, you will take the square root. Much like when you divide, it gets rid of multiplication via inverse operations. So the square and the square root will cancel, and x is isolated. And the square root of 100 is positive or negative 10. But since we're dealing with the length of a triangle, a length can't be negative, so we're just going to deal with positive 10. Let's try another example. In this case, we're going to identify the unknown side as a leg or as a hypotenuse. Then we'll find the side length. We'll write our answer in simplest radical form. So for number one, the question is x going to be a hypotenuse or a leg? Well, since it is not across from the right angle, but rather it is attached to the right angle, this is going to be considered a leg. So with our Pythagorean theorem, x is one of our two legs. The other leg is 3, and our hypotenuse, the part that's across from the right angle, is going to be 5. So 5 squared is 25, and 3 squared is 9. We can subtract 9 from both sides, so 16 is x squared. And the square root of 16 is 4, so x is 4. For number 2, x is our hypotenuse. It's across from our right angle, so x squared equals 4 squared plus 6 squared. And 4 squared is 16, and 6 squared is 36. And if we add 16 and 36, we end up with 52. When we take the square root of both sides, however, the square root of 52 ends up giving us a decimal. So let's try and simplify it using radicals and using a factor tree. So here we have x, and if we split the square root of 52 in parts, we can have square root of 4 times, let me double check that with my calculator. I want to say it's 13, but I want to be sure. Yes, times the square root of 13. And since the square root of 4 is simply 2, we can write that as 2 root 13. Now with the Pythagorean theorem, let's look at something slightly different. Where's it at here? There it is. Find the area of the isosceles triangle with the side lengths 10, 13, and 13. So let's draw this. 13, 13, and 10. We want to find the area. Well, the area formula for a triangle is 1/2 times the base times the height. In this case, we know the base is 10. We do not know the height. The height is not 13 because the height always needs to be perpendicular to the base. So we have to draw our own height in here. Now, we need to be able to find this height, which I will call x. Well, now we have two right triangles. And since this is an isosceles triangle, we know that this altitude is also a median, so it divides this in half. So these are both going to be 5. So we have 5, x, and 13. We can now find our missing height. So for this right triangle here, 13 squared equals x squared plus 5 squared. When we simplify this, 169 equals x squared plus 25. And we subtract 25 from both sides, so 144 is x squared. So x is 12. So that's our height. And now we can find the area. Area is 1/2 times the base of 10 times the height of 12. Our area is 60. And in this case, we're talking meters squared. Excuse me. And lastly, let's talk about some shortcuts with Pythagorean triples. These sets of 3 numbers form right triangles. 3, 4, and 5 will satisfy the Pythagorean theorem. So will 5, 12, and 13, 8, 15, and 17, 7, 24, and 25. Now, I have never seen 8, 15, and 17 used as a Pythagorean theorem, whether when I was in high school or college or teaching, so I don't focus on it too much because it's never used. But let's look at the other 3. Not only do these form right triangles, but multiples of these will also form right triangles. For example, if I multiply 3, 4, and 5 all by 2, I end up with 6, 8, and 10, which will form a right triangle. Or if I multiplied all these times 3, I would have 9, 12, and 15, which would form a right triangle. So if I know that 2 sides are 6 and 8, I automatically know the next is 10, using a triple. If I know one's 12 and one's 15, the other's automatically 9, using a triple. So it's a shortcut. Same thing with 5, 12, and 13 and all their multiples. 7, 24, and 25, all its multiples will end up being shortcuts for us to use. So let's do a couple of examples like that. We'll just use the triple. So we're going to find the hypotenuse. We have a 10, a 14, and an x. Well, there is no triple that has a 10 or a 14 in it. But let's see if we can reduce these using a common factor. We can divide 14 and 10 by 2. So this is 12 times 2, and this is 5 times 2. There is a triple that has a 5 and a 12. 5, 12, and the next is 13. So if this is 12 times 2 and this is 5 times 2, this should be 13 times 2, or 26. And if we would have used our Pythagorean theorem, so x squared equals 5 squared plus 12 squared, you would still end up with x is 26. You don't have to use a triple. It's just an option that's there as a shortcut if you'd like to do things a little bit easier on yourself. Let's try another one. Here we have 9 and 12, which are not parts of a triple. But let's simplify them by a common factor. We can divide 9 and 12 by 3. So 9 is 3 times 3, and 12 is 4 times 3. So I have a 3 and a 4. The next number in my triple, 3 and 4, is a 5. So if this is 3 times 3, this is 4 times 3, this should be 5 times 3. So x is 15. For number 8, 14 and 48, I can divide both by 2. So this is 7 times 2, and this is 14 times 2. So I have a 7 and a 24 times 2. I have a 7 and a 24. The next number is 25 in my triple, and all of these are times 2. So x is 25 times 2, or 50, and that is centimeters, and I neglected to write inches over here. So hopefully this video is a bit helpful. It's kind of brief, but the Pythagorean theorem is a review, and hopefully this was a review for you. If you have any questions, feel free to send me an email or see me before or after school.